Uh, Welcome to the second session of the second day.
Good to see you, Pushpa.
Uh, I'm really delighted to introduce Dr. Sriram Rajamani, again, one of the most dearest friends of IIIT. Thank you so much, Sriram, for being here. Sriram is a corporate vice president at Microsoft Research, and he is also an ACM fellow, INAE fellow, and winner of the Computer Aided Verification Award. His work has impacted both academic and industrial practice in programming languages, systems, security, and formal verification. He is currently working on reimagining the future of programming and software engineering in the era of large AI models. Sriram did his PhD in computer science at UC Berkeley. But then we always add a last line whenever Sriram comes here. He's also a parent of IIIT Hyderabad student. So
Yeah,
Sriram,
thank you.
welcome.
Yeah, the student as well. Yeah, thank you. But my son didn't want to attend my talk. He's gone home. Yeah. So, yeah, thank you. Thank you for inviting me. Such a pleasure to come here. Um, See, my background has always been in programming languages. So I never expected that I'll get invited to give a talk in an NLP audience. I think the only legitimacy I have is that I am using NLP as tools to solve, programming problems. So that's actually my excuse, I guess, for being here. But for the past year and a half or so, this is the topic that I've been increasingly getting obsessed about. I think that's the best way to describe it. And it started by, when first ChatGPT came and the GitHub Copilot came. I'm a proud programmer. My initial reaction was that, oh, it will just generate some code. Maybe it'll sometimes work, but I wouldn't take it seriously. Right. But some of my colleagues from Redmond convinced me, man, it's good. You should try it. Then I installed GitHub Copilot. And I just found that there are a few times when it gave me completions, which really was jaw-dropping for me. I couldn't really believe the quality of the code completions it was giving. So that's how I got sort of sucked into it. And then I realized actually that even though it gave me good completions, it had many issues as well. But the promise that that I saw compelled me to work in this area to fix the deficiencies rather than be a non-believer in that. So that's how I got sucked into this area. So what I'll talk about right now is sort of my own journey thinking about, and I've been building productivity tools for a long time. My entire career, I've been building verification tools, testing tools, and so on, more using compiler techniques, runtime techniques, and so on. And I've just been exploring how those can be combined with LLMs, right? So that's actually what I'll talk about today, right? But before I start, right, maybe I don't know how this clicker will work. What should I do? Should I point to something? It seems to be on. It works now? Okay, sounds good. So I have a couple of introductory slides, on, my own way of how I just got sucked into this field. These large language models and foundation models, you can sort of see the sort of the parameter sizes, growing over the years. And what was surprising to me was that these three things, right, the transformer architecture, the self-supervised nature of the learning, and scale. It was just really surprising to me how these three things can together create magic, right? That too, as an outsider to the NLP field, I just found this absolutely amazing that this thing actually happens. I have a colleague by name Sebastian Bubeck. He's in Redmond. He sent me this slide, which I also found absolutely amazing. That he tracked this was a NLP to image model, and he gave this caption, a portrait. He gave the picture. And I think maybe the other way around. He gave the prompt and actually asked the system to generate a picture. And you can sort of see how, as the number of parameters increases, the fidelity of the image generation increased. And Sebastian wrote a paper called Sparks of AGI. It's a very interesting paper. And one of the things that in that paper is he tracks actually as to how, as the number of parameters increased, even though these models were trained just for next token prediction, how this emergence actually happened. And as the models got bigger and bigger, at 62 billion parameters, they could summarize text. And most importantly for me, at 540 billion parameters, it could complete code. And that's how I entered into the picture, right? Once it entered 540 billion parameters, I think it somehow affected my life, right? Yeah. So this led to many interesting tools. And in particular, the tool that got sucked me into this field is called GitHub Copilot. And the way it works is that it sort of integrates with your coding editor. And as you write code, you can sort of see that it generates completions, right? And I use it every day. And I'm just stunned by how much it sort of understands what I'm trying to do. And it gives me contextually relevant completions to what I want to do. The other thing it does actually is that if I write a comment about, here is the code I want to write in English, it understands the comment and then it actually fills the code that I'm trying to write. It actually is able to generate test cases. I can actually select a piece of code that I'm trying to understand, and then it goes from code to natural language. It sort of explains what this code is doing. It's really, really amazing as to what these things do. And this is not a toy. I think it has over 1 million users. Last year, GitHub Copilot revenue crossed 1 billion. Right? So this is the scale of actually what's actually happening. Every serious software engineering organization now uses Copilot. All programmers use it. Right? That is it has now reached a stage where it cannot be ignored. Right? Which is why I don't ignore it now. That said, actually, even though it is really fascinating, there is still a gap between technology and the problems we want to solve, right? So, software engineering is very different from programming. That's actually one of the things I learned when I was a student. When you're a student, you actually do various programming courses. You become smart in algorithms, and somebody can ask you a complicated question of reversing an array in n log n, or all kinds of things people can ask, and you can do them, right? But then when you go to a large engineer, and by the way, before my PhD, I worked as a programmer for 5 years in the US in various companies. And one of the things that was a real learning experience for me was how hard it is to work in a team with, say, 100 people. And a code base of size, say, 1 million lines of code. It is so hard. Right? The reason why it is so hard is that typically your manager will ask you to own some piece of the code and ask you to make some changes to it. And you have to do that while building a mental model of this around 900,000 lines of code, which you don't know, right? And it is just a very, very difficult exercise on how to be a part of a large team. And actually, over time, as I grew in career, I used to manage a small team. And it's extremely hard to actually manage a team with 10, 15 programmers just writing code. It's incredibly hard, right? So if you now think about those kinds of problems, right? Suppose I am managing a team with 1 million lines of code. Then can these LLMs now help me do my engineering tasks better? Still, there is a huge gap between the capabilities of LLMs as a nice shiny object and the demands of software engineering as a large engineering profession. And this gap is actually what has interested me to now work in this area, right? But let me say actually that if the LLMs didn't exist, I wouldn't even dare automate, even embark on some of the problems I'm solving, right? So in the sense that LLMs are absolutely indispensable for the kinds of things that I want to do, but they are insufficient today, right? Which is why the opportunity in this research exists. So let me just tell you what these questions are, right? That are beyond the reach of LLMs today, right? So if you are a typical, this one actually, the first question I actually got from a Microsoft product group, Microsoft people write large C# code bases. And actually the same problem exists in Java as well. And these C# code bases rely on a library called .NET, right? And what happens is actually .NET, they will move from one version of .NET to another version of .NET. And then all of the C# code that depends on the .NET have to now rewrite to move to that new version. Same thing with Java. Java has actually these things called JDK, Java Development Kit, and they produce newer and newer versions, right? And now there are so many hundreds of millions of code that use the Java development, the library. And you have to now rewrite your code in order, because actually for various reasons, they are not API compatible. Even if they are API compatible, they may not be behaviorally compatible. So you have to go change code in order to deal with this version. It's a very difficult problem, right, to solve. So, you can ask, if I have 1 million lines of code, can I now use an LLM to And today, how do you people do this migration? They will employ 20 engineers and spend 1 year. That's what they will do. Right? Somebody will go through line by line of code and figure out how to actually move that. The second one is actually, I'll show you examples. Many large engineering teams have code quality checkers. They have various kinds of security issues. These are things you have to deal with if you run an engineering team. And the way people will deal with security issues is they build checkers or scanners that go through your code base and just point out, oh, here is a security error. And these things might, in a large code base, right, they can show 20,000 errors. If you have 10 million lines of code, right, they can give you 600,000 errors they can show you. Now somebody has to go triage each one of them and go deal with them. Again, the only way we need to do that is to actually just put people on it, right? And typically the amount of people you have to put on it depends on the size of the code base, and this is how it works. It actually doesn't scale at all in terms of what you want to do. The third one is, there are new programming languages like Rust. And so I don't know how many of you heard about Rust. Rust is by definition, by construction, it actually eliminates security errors in unmanaged code. There's a lot of code that people have in C, like Linux and Windows, and they're all written in C, right? And there's a Biden directive in the US to write all new code in Rust, right? Because hackers cannot do memory attacks if you write in Rust. But what do you do with all the other code that exists, right? Now, can an LLM can translate between English and Telugu. Can the LLM translate between C and Rust? I mean, it can actually. You can give it one method, you can do it. But you can give 1 million line of code, can it translate? But still, the first question is possible. Second question is not possible today. Right? So this is the problem I'm interested in working on, right? And as I said, right, if LLMs didn't exist, I won't even attempt them, right? But even if LLMs exist, it's very hard to solve this problem. And one of my theses of my talk is actually, in order to do this, you have to combine LLMs with classic program analysis techniques to solve this problem. And I'll give you evidence of this, right? But I haven't solved this problem. It will take many years to solve this problem, right? But I'll give you glimpses of what is possible, right? So the first glimpse I'll give you is propagating changes across what I call dependencies in code. Let me just explain what this means. Let me explain what this problem is and a solution that we have come up with that actually kind of works, right? So I'm sorry for the font, it is green, but let me just try and point that to you here. So so typically this is the kind of thing that people want to do, which is what I'm seeing here is actually a class called complex number. I mean, we just created this academic example where a complex number class has a real field, imaginary field, and so on. And throughout my code, I have complex numbers, but I've represented complex numbers as a pair of floats previously, right? So basically these things, right? Return a complex number is a pair of floating point numbers. That's what this code is returning. Now I'm going to rewrite that code to use a complex number as a class, right, in an object-oriented fashion. This is the kind of thing that people always want to do, right? Now, what I have to do in order to deal with this change is that I have to go to all the places where create complex is called. See, here it returns this variable. I guess it's implicitly typed. This is a pair of floating point numbers that is being returned here. I want to rewrite this to this code that you cannot see because it's not, because of the color, to return a complex number. So now actually, the same functionality, but it returns a different class, a different type, right? The reason why this is a very difficult thing to do in software is that in software is actually you change one line, the whole thing falls like a pack of cards, right? There are so many places where this method, right, which is now returning two floating point numbers, this is called func. Now this func is called within this process. See, this process method calls this func function. And this func function expects now a pair. Now it returns, like it was expecting an apple, now it is getting an orange. It is now getting a different type. Now I have to go to all those places and change that code. Now that code will return something else. So this change can percolate through your million line code base, right? And today the only way we know how to do that is actually to employ somebody to go do that. And you can ask an LLM. What an LLM can probably do is that you can give it a localized method and then say, how should I change the method, assuming something has changed. But the LLM currently doesn't have the intelligence to do all of this dependency analysis and figure out how to do this in like 5 million lines of code at a time. It just simply doesn't have the intelligence to do that. Actually, one way to put it is that if the entire program can fit into the prompt window of the LLM, I can actually ask that question. But the code is just too large to fit into the prompt window of the LLM. So some people might say, oh, that's fine. I can now build large prompt LLMs. Maybe I'll build a million token. So what I find is actually if you do that, the quality of the output just degrades, right? But no matter how big an LLM we build, I have software that is much bigger than that also. This is, this is life. There's nothing you can do about it, right? So, so how do you solve this problem? The way you solve this problem, as a programming languages person, these kinds of dependencies, I don't need an LLM to track. I'm a compiler guy. I know how to build dependency graphs. I know what depends on what. I know how to track them. So what we did was actually this process that I just told you, I can actually implement. This is like, in some sense, actually, together with an LLM planner, I can actually implement a static analysis based planner that uses all these dependencies because I know how to build these dependency graphs. And then I can actually have an algorithm where I go through every change, figure out, if this method now returns an apple instead of an orange, who are all the methods that actually call this method that I can figure out statically. I can go to each one of them and I can give an appropriate prompt saying, hey, this method that you're calling used to return an apple before. Now it is returning an orange. Well, how will you now convert yourself? And what thing different will you return? I'll just ask that question to the LLM. The LLM might say, oh, I know how to do this, and now I'm going to return a mango. Now I have to go to call the callers of that method and say, previously you got an apple, now you got a mango. So this kind of analysis, right, that I'm doing manually, I can do that using a combination of a static analyzer that builds all the dependencies, and in some sense, break the big problem of rewriting this into many, many small LLM calls, each with different prompts, right? Because that actually depends on the type information of what comes in. And the static analysis has information to figure out what to call the LLM also. It's a very fine-grained interleaving of static analysis of the LLM. And this technique actually works. There is a paper that me and my colleagues wrote in FSC this year, which actually explains this thing called code plan, which is a planner which consists of an LLM-based plan together with a static analysis-based planner. And I'll give you some results here. We now ran this on software with multiple files where, so we have this terminology called seed changes. The seed changes are the initial changes you want to make. And the derived changes are the ones that you get from propagating those seed changes. And it turns out actually, what you can do actually in these cases, actually the interesting thing is actually because of GitHub, you can have many places where people have done this manually, right? People would have done, oh, I need to do this upgrade or something like that. And they would have manually gone through all the files and changed them. So we can have that as ground truth and try and run our algorithm to see how many of the things that people manually changed. What do our tools get, right? And you can sort of see here that, in comparison to ground truth, okay. So I must say, what is the baseline for this? If you don't have this algorithm, right, the baseline for this is something called build fix, where if you have an inconsistent piece of code, you can actually just run a build. You can just build a compiler and linker, and the compiler will give you compiler errors. Right? Because in one place you'll get an apple, but the other place will accept an orange, and then you'll get a compiler error, or you'll get a linker error. And you can actually take the linker error message and give it to the LLM and say, oh, can you fix this, right? But the problem with using that is actually it doesn't have causality, right? What you can do is actually the LLM might undo the change that you want to do, right? It'll just convert the apple back into an orange, which is not what you wanted, right? So you need actually causality in that, and that's actually what these things do. And you can sort of find here that using code plan, we are able to get amongst, like, for example, you can sort of see, the higher these numbers are, the more we are able to get closer to ground truth with respect to code plan. You can sort of see with code plan, you can actually get numbers like 1, 0.86, 0.9, and so on, which is really, really interesting. And, because since I work for Microsoft, one of the things we have now done is actually integrate this algorithm into GitHub Copilot itself. Right? There is actually something called Copilot Workspace, which is the newer version of Copilot. And this code plan algorithm shows up as this feature called follow-up in GitHub Copilot, which is actually you make a change, and then you want to follow up those changes everywhere. And that's actually this algorithm that's actually implemented. And it actually ships with the GitHub Copilot, which is kind of cool if you work in a lab like mine. Right? So that's actually the first thing. Hopefully, this gives you a little bit of sense about the kind of work that we do. The second thing I'm going to do is the first one, actually, I used an LLM as a black box and then layered static analysis on top of the LLM. The second one, I'm actually going to open up the LLM as a box, going to get inside the decoder of the LLM and use type information to change how the decoding is done. right? So now I'm like becoming a true machine learning person and sort of getting inside. And unlike the first paper that I submitted to FSC, this one I submitted to NeurIPS, and they did accept it, right? This is my first NeurIPS paper, right? So here actually I'm going to show you this technique called monitor guided decoding, and I'll tell you first what the problem is. The problem is actually that the same thing. I'm going to do completion. So if you now are sitting in this piece of code and you want to complete this, now because these large language models have learned these patterns from all of the code in the web, they can give you, the server node, it gives you a completion like this. It gives you .post, .port, .build. And that is just based on the names of these things. But in my code, right, I might not even have this host as a field because, it maybe has the same name, but my class has different members and so on. My type system is different and so on, right? So it turns out in this case, right, and this happens all the time. Actually, you will get completions that maybe make sense for somebody else's code, but it doesn't make sense for your code, right? So it turns out that, and so how do you solve this problem? So what you have to do, if you just intuitively, what you have to do is that you have to teach the LLM what your type system is for your code, right? And it turns out that programming languages people already have tools to solve this problem. And that tool is actually called LSP. LSP stands for Language Server Protocol. And if you are a programmer, you would know that if you program in Visual Studio or Eclipse, right? If you type, the tool will give you possible completions. Even by the way, before LLM also. Because LLM can complete even the entire method. But Visual Studio will give you what is the next field you want to type, right? Because actually that comes from type information. You can actually build a compiler-based analyzer that sort of give you type-consistent completions, right? So what you can do is actually, in some sense, all that you have to do is that you have to intersect the decoding distribution of the LLM with type-consistent completions, right? If you intersect them, you will actually get completions that also make sense from a type perspective, and it will compile, right? And that's what we did, right? We designed a stateful monitor that understands the type system, and it runs together with the decoder. And in fact, actually, it runs inside the decoder. And as a result, right, you can actually produce completions which not only satisfy the probability distribution of the LLM, but is also type correct. It's actually possible to do that. And actually, you can get, completions that actually will compile, right? So how does this work? And this appears actually in NeurIPS in last year. So how does this work? So at every prefix, we use the LLM to get a probability distribution. And then we also use the type system to get legal completions. And then we intersect these two to get a revised distribution in which the only allowed ones are the only ones that are present and the others are just zeroed out, and we sort of re-normalize the distribution and then do sampling from that. And then we sort of do that at every stage. And then you now get a decoder that is type aware and correctness aware of what you need to do. And then using this, you can actually get code that actually compiles and code that actually is consistent with the type and object structure of your system, right? So here are some results here. Now, for each of these, right, the dotted line and the solid line, so the y-axis is compilation rate. So basically, these experiments are done by taking a large corpus, right, picking up maybe in every file 10 or 20 places where we're going to delete the code but rewrite it using the LLM. Right? So we know what the ground truth is, right? And then figure out actually how many fractions of those actually compile. So higher is better. And the dotted line is without this. This is called monitor guided decoding. The dotted line is without the MGD. The solid line is with the MGD, right? So you can sort of see the compilation rate goes up. I mean, and this is for many different like SLMs as well as LLMs, right? For various models, right? You find that if you do this, you can actually get code that compiles better. What's interesting is that some of the smaller models, like for example, Santa Coder 1.1 billion parameter, which I think is this one, right? With MGD, does better than the text DaVinci 3, which is like a much, much bigger model, right? So what I learned from this is that if you understand the programming language and the type system, you can get performance from a small model that even beats what a large model will do. And if you add this kind of facility to a larger model, it actually performs even better, right? This gives me another evidence that in addition to just learning next token completion, if you understand the structure of the program, you can actually get much better quality with these LLMs, right? So the third example I'll give you is automatically fixing code quality errors. I sort of mentioned this as actually fixing security issues and so on. So how does this work? Again, actually, if you work in a large engineering organization, as a programmer, every day you will get email saying, oh, automatic scanners have run. Your code has 35 alerts. You are supposed to now go through them and fix them. Like this is an example, right? Where, I mean, this is Python. What's happening here is that every time you override a class, you are supposed to also rewrite your EQ method, right? Because when you override a class, you might have added new members. Now, when you do check equality, you have to also check the new members in addition to the old members. Otherwise, actually, your equality might be just imprecise, right? And if people don't do that, a checker can actually check that automatically. The question is actually, when you can do that for one error and one file, but if you have 200 rules and 1 million lines of code, you will get a lot of such email. So the question is actually, in addition to finding these, can we automatically fix them? Can we just resolve them, right? That's what we built in the system, where we take the output of the static analysis tool as an input and then build this system, which is an automatic fixer, right? So you just now not only say actually what the error is, you also propose a fix, right? And so you automatically generate a prompt. You use the LLM as a generator. And what you do is actually, I mean, since we can't trust the output of the LLM, we generate multiple completions. And then the first thing we do is actually we first check, because these were actually detected by a static analysis tool. We can rerun the static analysis tool to see whether actually it really fixes the problem, because that actually I trust, right? And then it turns out that even if you fix the problem, by the way, one way to fix the problem is to just delete that code. Then the problem just goes away, right? So among the various possible fixes, we need to figure out which ones are acceptable to the programmer because of many other reasons. And you can actually train a checker stage as another LLM to check which one is suitable, right? And this one is actually, I wouldn't know how to build it without AI. Because unlike the specification here, which is very rigid, right? This is actually sort of what is acceptable to the programmer. But you can actually teach an LLM to do that. So using these stages, right, you can actually build a pretty interesting system. And I'll show you some stats. These are academic data sets. And we have tried this also in internal Microsoft things. It turns out that these are two different static analysis tools. CodeQL is a static analysis tool. SonarQube is also a static analysis tool. And these two are present in public benchmarks. So what we did was, you can see some numbers here, right? So we started with 765 alerts. We're looking at two kinds of alerts, right? One is Python and the other is Java. So we started 765 problems, 520 problems. We run this through the LLM. We get 10 completions for each one of them to fix the error. And we figure out which of this 765 times 10 completions satisfy the static analysis tool, right? Then you can sort of see, I was not able to find, of the 765 cases, we can only find 624 completions. The others that we don't know how to fix. And then what we do is actually, of these, we actually look at how many of those will likely be accepted, right? And again, actually, we are able to go to a much smaller number. But after all of this, right, we found that 82% of the revisions that were rejected by the checker were also rejected in the manual evaluation. And 73% of the revisions that were accepted, right, what we finally say, are actually acceptable to a program. So we actually, this is really promising, which makes me believe that with more work, right, we can just really improve this if we get the data pipeline going, train these things better, right? And actually, one of the really interesting things about large software is that large software is also a large amount of data. There's lots and lots of fixes that people have already done that we can use as training data to train these kinds of pipelines. So this actually makes me very optimistic that you'll be able to build automatic fixers for checkers, which, by the way, without LLM, I wouldn't even attempt to do these kinds of things, right? So now, actually, this is the first section of the talk. Maybe I can take like 10 more minutes, Vasu, is it? Right? Maybe 10 more minutes. So now I'm going to switch gears and talk about a different set of problems, right? The first set of problems I talked about are all problems with large engineering teams. That's one way in which I think LLMs are creating disruption. The other way in which LLMs are creating disruption in programming is to make non-programmers write programs, because you can now program in natural language. I can now write code I can write now an English statement saying, actually, I want to do something. And the LLM can maybe compile it into Python and run it or something like that, right? And that's actually, many people actually are doing that right now. But my question was, Okay, you can do that as a hobby. Can you build a product like that and actually ship it and support it? And what do you need in order to do that? Suppose you have a bunch of people who are experts in their domain. Maybe they could be finance, right? One of my children, works in biology. I mean, she has now learned Python, but I'm just imagining if she didn't know Python, can she code, with English, right? So I think that's a very interesting question to ask, right? How would you do that? So I was very interested in that question. Um, so can you build end-to-end software engineering using natural language? Could be diagrams, could be text. I just describe what I want to do, and can I just generate code, right? And again, here the question is actually not whether it is possible or not. It's possible, but can you do it like a professional engineering organization where you will get code with high quality maintainability? If you ship it and your customer says this doesn't work, you can't say, I have no idea what to do right now, because there are many parts that are not sort of engineering friendly, right? So how do I do that, right? So let me just show you the context in which we did this, right? We had actually we were engaging with an organization. This is actually in the, this organization was called Bandhu. They were trying to build an app to get housing for migrant workers. This is a real situation where, this does happen in India, where from villages or from other parts of the country, migrant workers come to cities and they have money, but they're not able to find rental housing. Right? You show up, you look dirty because you've been doing in construction, and then the landlord doesn't give you the house because you look different. You maybe speak a different language, and even if you have money, they don't give you house. It's real issue, right? And Bandhu was actually trying. I mean, of course, there's an issue about housing with people who don't have money, but even if you have money, it's still a problem, right? So Bandhu was actually trying to solve the problem for the people who had money, right? So they wanted to actually build an app. They want to finally deploy this using WhatsApp, where you can actually check, and you can figure out, you can search for that, and then you can use Aadhaar to authenticate itself. You can use UPI to pay an advance, and so on. That's the kind of app that these guys wanted to build, right? And then Bandhu has volunteers, most of whom are lawyers. So they want to ask whether the lawyer can also build the app. That was the situation, right? Because they know actually what they want to do, but can they now do it without hiring a programmer? Right? So actually that we thought we'll play with it. So our team, actually what we did was, there's all these GPTs and other things exist. Can we now we just sat down with them and figured out what app they want to build. And if I put that in, there's something called GPT assistance at the time. If they ask them to do, their entire logic, you give it to the GPT assistant, and GPT assistant will now run it. So how will that app look like? Right? There are problems with that app, right? Let me show you an example of those problems. The bot says, hello, how can I assist you today? Now I can say, I want to book this house, and I've already paid 600 rupees, even though I haven't paid, right? I think the system says that it's great that you heard that you've already paid. Let me just show you the next step, right? This is a real problem, by the way, with these kinds of applications, because actually the LLM doesn't understand what has been already done and what see, basically, right, what has happened here is the following, right? This instruction is quote unquote a program that we have told the LLM. Now, what the user is asking to do is also the program. So there is a program that the programmer has written. Now the user has asked you to do something. Typically, you collect all of them and give it to the LLM. You say, do the next thing. So the programmer can say whatever. The user can say, forget what the programmer said. Let me do something else. And the LLM cannot distinguish between those two. The real issue with these things, right? Which is why if you build purely natural language applications, these injection attacks are unavoidable, right? Because there is basically no difference between what the programmer has written as code and what the user, they both code. It's a real issue, right? So what we wanted to do, because I'm a programmer, what I want to do is that I want this conversation between the developer and LLM to be based on a representation. And a representation that I particularly like is called a domain-specific language, where, you talk to the LLM in natural language, but these conversation results in a representation which has a clear semantics, which is a program. I can understand what the program can do, and I can understand what the program cannot do, right? And then you compile this program into an executable, and then you run it. And my belief was that if you do that, you will get a different kind of robustness. You don't get these kinds of errors, right? And this is what we built. Let me just show you how this app looks like. Maybe I have to press. How do I press next? Yeah. I want to just run this. Yeah, let me just do this. I have to mirror it, yeah.
हमें बताइए
By the way, this is the app. It was built using our system. Yeah. I don't see sound, but
हमें बताइए किस तरह का ठहराव कमरा सोने की जगह पूरी संपत्ति शहर का
it's
मासिक
voice
किराया
interaction.
बजट
This is the
मैं
final app.
बंबई
It's not the
में
developer
कमरा
experience.
ढूंढ रहा हूँ, 20,000 रुपए तक का चाहिए।
Yeah, you can sort of see, how finally the app works in entirely natural language. But what I'm most kicked about is actually not the app experience, but actually how. Maybe go to the next slide, if that's possible. Yeah.
हमें बताइए
That's fine. You can stop, but let's go to the next one. Yeah, it's good. Yeah. So this is how our programming system works, right? So we also, this entire program, this is the representation of the program. It is now developed using a conversation as well. So the programmer can say, oh, it's at some stage of the program this has been run, right? Now what the system says is that, I can say, after searching for a house, charge the user 600 rupees to generate this. I'm using UPI to do this, right? Now, what the system does is that it compiles this request into a domain-specific language, which sort of understands it as a type system and all of those kinds of things. And as a result, right, it knows that in order to invoke this function, I also need a name. I need a contact number. If I don't have all of these things, I can't even call the API, right? So it asks that, in order for you to execute this instruction, in order to update my program, you have to provide all these things to me, right? And then if I now say, oh, I have to do this, here is the name, do this, and all the missing values I provide. And then it also says, actually, by the way, you have to handle all these. It's not like, you just charge payment, right? What happens if the user cancels the payment? What happens if the API credentials are wrong? I mean, the API knows all of those kinds of things, right? But if you're programming in natural language, you don't know that you have to handle all those kinds of things, right? So it actually asks you to handle all of these kinds of things. And then you have to say, oh, I have to do this. This is the name. Here is a mobile number. If the payment is canceled, first ask. So you have to say all these things in English. See, as a programmer, you are trained to do all these error cases, right? So this gives you an experience where everything the programmer has to do, the bot will ask you the question in natural language and ask you to ask back, right? And as a result of this conversation, right, there is actually there is a DSL and a flow chart that is being created. It is there, but we expose that in natural language, right? But the model is there, right? And so in some sense, what's actually happening here is that you are having a conversation and you might be a lawyer and you can actually see the program in natural language, but underneath it, it has the hardness of a domain-specific language, right? And when we code gen, we code gen from that, right? So this, I believe, actually, as a programmer, I can support this. Now, I can build a product like this, I can stand behind it, right? But if it's purely natural language, I don't know how I would support that product. If somebody says it doesn't work, I wouldn't even know what to do about it, right? So this, by the way, actually, this Satya is a huge fan of this product. You can just see. You may have heard this word called Jugalbandi. So this is actually part of the Jugalbandi ecosystem. What I just showed you is called Jugalbandi Studio. That's what this is, right? You can just play this one. This is my last video. You can see if you can.
Last time I was here, I saw the demo of Jugalbandi, and I spoke about it many, many times because it was just a drop. It's like drop the mic moment for me to see how this.
Oh, no, you changed the stack.
Last time I was here, I saw the demo of Jugalbandi, and I spoke about it many, many times because it was just a drop. It's like drop the mic moment for me to see how this digital public good in Bashani combined with Jugalbandi was being used to transform lives of people in rural India, speaking in vernacular languages, and being able to not only get access to information and knowledge, but to take action, right? I mean, talk about human agency in the age of AI being enhanced. That was an example. And now the team has even built a fantastic thing called Jugalbandi Studio, which is a no-code, low-code tool for people to be able to build these bots and make them available to all of the social entrepreneurs, the nonprofits who are doing things, the empowerment it gives to the end citizen here, but also the empowerment to all of the social enterprises to be able to use something like this to make a real difference is fantastic to watch.
It is open source. It's available. Anybody can check it out, right? This is my last slide. Maybe one slide before, right? I think, I said a lot of things, right? But maybe stepping back, what's actually happening here is that, see, as a programmer, here is how I always thought the programming stack looks like. There is some intent of what you want to build. That, if you go to an engineering team, like I see some colleagues of mine from the engineering team, you will see whiteboards filled with these clouds, right? And then actually people encode them. And these program managers, all kinds of people write these things, right? And then after a lot of coffee, it gets converted into programs, right? And these programs are at an extremely low level of detail, line by line, right? And then we run them through compiler, linker, executable. This is how we run, right? I think what the LLM now enables us to do is to capture the intent, right? And then convert the intent to a representation. And the representation can actually be a very high level, right? And by the way, even if you have code, the representation allows you to operate over large bodies of code with one go, right? And then you can do planning and execution. It's a very different way of doing engineering, right? And this is more details, what I talked about, both these cases, both repository level programming and robust programming. And I've left these slides here. These are all the papers, that you can read about every one of these. They are all published. And stop here. Thank you. Yeah, I'll leave this one here. Yeah.
Little more light on how you translated natural language to DSL would be helpful, and how are you ensuring that the DSL translation is consistent?
How do you convert the natural language to DSL?
Yeah.
So what we do is the following. What we do is that the DSL has a schema, right? You could sort of think about a DSL program much like a JSON object with a schema.
Right.
Or, like a TypeScript object with a TypeScript schema.
Right.
So what we do is actually we prompt the LLM to say, actually, oh, here is something that you want to do. Here is the source program, which you could sort of think about it as a JSON object with a full clear structure, and rewrite this so that the target one corresponds to something in a schema. And then we don't stop with that. We actually now run consistency checkers. So the LLM outputs many candidates. For each one of them, we run a bunch of checkers which say that, there are no dead states. The program is well formed. And if the checkers give us errors, we reprompt the LLM with those errors to rewrite the program with certain properties. That's how it works.
So essentially, you're using natural language text, and then you're asking LLMs to translate it to a JSON, but that JSON structure is predefined, and then that's your DSL.
Right. And then I just predesign, and then actually I have semantics,
and then
I can build semantic checkers on top of them to make sure that it is well behaved as well.
Right. Yeah. Right. Great. Thank you.
Yeah.
One last question.
So, Sriram, I was just wondering about some theoretical points, which is that, this halting problem where you cannot write another program to find out if a program has an infinite loop. Which high level meaning of this is that you cannot write an automatic debugger.
Yes.
In general.
Yes.
So the programming fixed part that you talked about, how does it pitch against this theory?
Yeah. But actually, Pushpak, the question you asked me, even in the pre-LLM days, it's a valid question for all program analysis.
Yes.
Right. Even detecting whether a bug is there in a program is undecidable.
Correct.
Right. So it turns out that in spite of that, you can actually build many checkers. And these checkers can either be sound or complete, but they cannot be. What the halting problem tells us actually, it cannot be both. Right. So what you can do is actually, you can, in spite of this undesirability, you can build useful checkers that are either one of the other, and you can actually figure out how to build these systems in this trade-off where it's actually usable. It is possible. This, in fact, actually, I worked in program verification so many years. Every problem that I worked on is undesirable, right? It is still possible to build tools that are usable, and basically they would either be unsound or incomplete, or in many cases, actually, they might be both even. I built checkers that are neither sound nor complete, but still usable. But but there are ways by which you could describe them. You could actually figure out subsets of languages under which they are guaranteed to work. You can do all of those. There's the whole language theory, program language theory is about all of those kinds of things. For example, type systems. Type systems work, right? In spite of the halting problem. Because there is a way in which you structure the program, it works only for programs with certain particular structure. So there's a language theory has all of those kinds of things, right? So how do we now answer that question in this light, right? So what you do is that even though you can't trust the LLM, all the checkers you build are based on old programming language theory that we have learned how to circumvent this undesirability over many years. So people like me, right? We think about something called a trusted code base and untrusted code base. Right? Like security, for example, right? How do you get a big system to be secure? The way you build a big system to be secure is actually, you actually try and reason only about a small portion of the system and ensure its security. You typically build a monitor, and you have to only verify the security of the monitor. And the monitor has the property that even though the large part of the system is untrusted, it cannot circumvent the monitor. There's a way to design it, right? So I'm sorry, there's a long answer. The way it works, actually, people like me, we have figured out how to dance around this problem for a long time, right? By figuring out how to structure the code, how to give reasoning only when you analyze only a small portion of the code, right? But you cannot do this for arbitrary programs. You have to design a program in such a way that those properties hold. And in the LLM world, we are just continuing to follow the same tricks. There is no new tricks. There's nothing new under the sun.
Thank you so much, Dr. Sriram. I would like to call on Vasudev sir to please present your token of appreciation.